Welcome to RS3 version 2, tutorial 7. This tutorial will demonstrate some of the consolidation features of RS3. In part 1 of this tutorial, we will demonstrate the extensive 3D modeling capabilities of RS3 version 2 and the tools available to create complex geometries. To begin, run RS3. To create a new model, click the New Project icon. We will begin by modifying the project settings. Click on the Project Settings icon. In the Units tab, set Units to Metric, stress as kilopascals. Select the Groundwater tab. Set the method to Transient. Activate the Define PWP method by Stage checkbox and deactivate the Scale Tolerance according to Time Units checkbox. Select the Stages tab. Change the number of stages to 13. Set the PWP method for stages 2 to 13 to Transient. Set the time for each stage as follows. Select the Solver Options tab. Change the analysis type to Coupled, BO. Leave the solver type as automatic to ensure accurate results. Click OK. Next, we will assign the materials and properties of our model. Select the Define Materials icon. Enter material properties as follows. For Material 1, change the material name to Embankment Fill. Set the initial element loading to body force only, and set the unit weight to 18 kilonewtons per meter cubed. In the Stiffness tab, set the Poisson's ratio to 0.2. Leave all other parameters at their default values. Select Material 2 and change the material name to Sand Fill. Set the initial element loading to field stress and body force, and set the unit weight to 18 kilonewtons per meter cubed. In the Strength tab, change the friction angle to 28 degrees and set cohesion to 0 kilopascals. In the Stiffness tab, set the Young's modulus to 25,000 kilopascals and change the Poisson's ratio to 0.2. Leave all other parameters at their default values. Select Material 3 and change the material name to Silty Sand. In the Strength tab, set the initial element loading to field stress and body force and set the unit weight to 18 kilonewtons per meter cubed. Change the friction angle to 33 degrees and set cohesion to 0 kilopascals. In the Stiffness tab, set the Poisson's ratio to 0.2. Leave all other parameters at their default values. Select Material 4 and change the material name to Dense Silty Sand. In the Strength tab, set the initial element loading to field stress and body force and set the unit weight to 18 kilonewtons per meter cubed. Set the cohesion to 0 kilopascals. In the Stiffness tab, set the Young's modulus to 25,000 and change the Poisson's ratio to 0.2. Leave all other parameters at their default values. Select Material 5 and change the material name to Silty Clay. In the Strength tab, set the initial element loading to field stress and body force and set the unit weight to 18 kilonewtons per meter cubed. Change the friction angle to 25 degrees and set cohesion to 15 kilopascals. In the Stiffness tab, set the Young's modulus to 9,000 kilopascals and change the Poisson's ratio to 0.2. Select OK. We will now begin creating the model geometry, starting with the slope profile. Ensure the Geology Workflow tab is selected and select the Draw Polyline icon. In the Draw Polyline panel, select the XZ plane orientation. To draw the structure, enter the following UV coordinates, pressing Enter between each pair. Once finished, click the blue checkmark to close the pane. Select Polyline 1 in the visibility pane, then select the Create Polygon from Polyline icon. Select Create Polygons to transform Polyline 1 to Polygon 0. We will now need to extrude the polygon. Select Polygon 0 in the visibility pane, then select the Extrude icon. Change the direction coordinates to 0, 1, 0, and depth to 50. Click OK. We need to create a copy of the slope profile to cut the model with later, so select Polygon 0 Extruded in the visibility pane, and select the Copy Geometry icon. Set the number of copies to 1 and the spacing to 0. Click OK. We will now create the embankment. Select the Draw Polyline icon. Select XY plane orientation. Set the origin coordinates to 0, 0, -12, then press Enter. To draw the structure, enter the following UV coordinates, pressing Enter between each pair. While you are in the Draw Polyline pane and have finished closing a shape, you can enter a new polyline without closing the pane. For the second polyline, select XY plane orientation. Set the origin coordinates to 0, 0, -1, then press Enter. Enter the following coordinates, pressing Enter between each pair. Once completed, click on the blue checkmark to close the pane. Now, select both newly drawn polylines in the visibility pane, then click the Loft icon. Activate the Close Top and Close Bottom checkboxes, then click Loft. In order to model staged embankment construction, we need to divide the embankment volume. Click on the 3D primitive geometry icon and select Create Plane. Set the plane orientation to XY, then select Loft in the visibility pane. Under Plane Size, select Fit Plane to Selected. Change the width to 50. Under Plane Definition, change the origin Z coordinate to -2.4. Click Create Plane. Keeping the Create Plane dialog open, change the origin Z coordinate to -3.8 and again select Create Plane. Repeat this once more, this time setting the origin Z coordinate to -5.2 and selecting Create Plane. Click Done once finished. Now, to capture the extents of the model's external boundary, the embankment must be merged with the slope. Since they are made of different materials, we also need to create a cutting plane between the merged bodies. Select Polygon 0 Extruded Copy 0 and Loft in the visibility pane. Click Geometry, 3D Boolean, and select Union. Click OK. Select the Union body in the visibility pane and select Geometry, set as External. You have now completed the construction of the model geometry. This concludes part 1 of the embankment consolidation tutorial. Click here to continue on to part 2 to complete model creation and analysis, or click here for more details.